Jai Hind students, I am Shiwani and today or in this lecture I will discuss the introduction of spectroscopy and Lamberts Law. The references are taken Organic Spectroscopy by Y.R. Sharma, Engineering Chemistry by Jain and Jain and by Shashi Chawla. So, the first, what is spectroscopy? Spectroscopy is a branch of science which deals with study of interaction of electromagnetic radiation with matter. That is, if we take the matter and interact with electromagnetic radiation, this interaction or what happened, it comes in spectroscopy. The most consequences of such interaction is that either energy get absorbed or emitted in a discrete amount of quanta, that is h nu. Spectroscopy is one of the most powerful tools used for study of atomic as well as molecular structure and also used in analysis of wide range of samples. So, in spectroscopy, first is what is spectrum? We know that the energy level of ground state, these are called, or energy level of lower energy, these are, it is in ground state, and higher levels are excited state. So, if the atom or electron, it absorbs the energy as goes from ground to higher energy state, that is absorption spectrum occurs. So, in absorption spectrum, the transition of atom or electron from ground state to higher energy state. In a reverse phenomena, if the transition occur from higher energy state to ground state, that emission spectrum occur. So, in absorption spectrum, if we check the 7 lines, the particular wavelength of light which get absorbed, it appears as a dark line. While in emission spectrum, the overall is black, but the light or the wavelength light which get emit, it appears in the respective color. So, there are two types of spectroscopy. First is absorption spectroscopy and emission spectroscopy. While on the basis of energy level or atomic level, it may be atomic spectroscopy or molecular spectroscopy. There are few complex terms. First, fluorescence, that is absorption of radiation to excited state followed by emission of radiation to lower state of same multiplicity. In phosphorescence, the same definition, that is absorption of radiation followed by emission of radiation to lower state but having different multiplicity. In singlet state, the spins are paired, that is no angular momentum or no net magnetic field. While in triplet state, the spins are unpaired and which shows net angular momentum with net magnetic field. So, these 4 terms are complex terms which are used in spectroscopy. So, there are 2 spectroscopy. The first is absorption, second in emission. In absorption, the amount of radiation which is absorbed, it depends on the structure of molecule. That is, which type of spectroscopy, the spectroscopy which is used to find the structure of molecule, it is generally absorption spectroscopy. And the number of molecules interacting with the radiation. The study of these dependency is called absorption spectroscopy and the examples are UV, IR, NMR, etc. While in emission spectroscopy, if the sufficient energy gets impinged upon a sample, the outer electron of species, it will raise from the stable ground state to higher energy level. And these excited species rapidly emit a photon and return to ground state. And the type and the amount of radiation which is emitted, it is studied in emission spectroscopy. For example, atomic emission spectroscopy, molecular emission spectroscopy, or fluorometry. And the spectroscopy which gives the information at an atomic level, it is atomic spectroscopy, and which about a molecule is molecular spectroscopy. So next is, what is the basic theory? So if suppose this is a matter, and if matter is interact with or irradiate with electromagnetic radiation of particular wavelength, few part of it get reflect, few part of it get absorbed, and rest transmitted or scattered, or it photoluminescence, that is a sample or a compound, it glows. So, but in this spectroscopy, we basically discuss this point, that is how much amount of get absorbed or how much amount it get transmit. So that is in UV visible, IR, microwave or NMR, we studied absorption as well as transmittance. Now, what is electromagnetic radiation? We know that the radiant energy, it has wave nature and associated with electric vector as well as magnetic vector, and both vector, these are perpendicular to each other. And electromagnetic radiation is a form of energy that is transmitted through space at an enormous velocity. So the radiation which has both vector perpendicular to each other is termed as electromagnetic radiation. EMR is alternating electrical and associated magnetic force field in space. So electromagnetic wave, it has electric component as well as magnetic component. The two components, they oscillate in perpendicular plane to each other and direction of propagation of the radiation. So there are few terms which are used in electromagnetic radiation. The first is wavelength, shown by lambda, and it is the distance between two or successive throw or crust like this. So the distance between two throw or crust, in it is measured in nanometer, meter or angstrom, etc. Second is frequency. Frequency means the number of complete wavelength passing through a given point, or we can say the number of cycle per second. It is shown by nu. Wave number, it is reciprocal of wavelength 1 by lambda and shown by nu bar. In electromagnetic radiation, if we find the energy, and this energy is equal to h nu, where h is the Planck constant, 6.626 into 10 to the power minus 34 joule second, and nu is the frequency which is in second inverse. In terms of wavelength, nu is equal to c upon lambda. So we can say E is equal to hc upon lambda. And since 1 upon lambda is nu bar, so we may say E is equal to hc nu bar. This is basic instrumentation of a spectrophotometer. Light source, we get the light from the light source and then pass through a prism. It divide in a spectrum, and then we pass through a slit and then sample. Then we get a spectro diagram or spectra. Now, if we check the electromagnetic radiation, because in spectroscopy, we read either UV spectroscopy, IR, suppose NMR, microwave. The basic differences, all are electromagnetic radiation, or in all irradiate with electromagnetic radiation. But if we choose a wavelength of this range, then it is called UV spectroscopy. If we choose a radiation of wavelength which comes in IR, then it is termed as a IR spectroscopy for radio and for microwaves. So if we check the electromagnetic spectrum in increasing order of energy, then first radio waves, microwaves, IR, UV, visible, then X-rays, gamma rays and cosmic rays. This is the increasing order of energy, and since E and lambda are reciprocal, so we can say it is the decreasing order of wavelength. That is, the wavelength of UV visible is less than wavelength of IR and then microwave. The frequency of radio waves, it is in region 10 to the power 6 to 10, microwave 10 to the power 10, 12. So here we see that increasing order of frequency. Why? Because E is equal to h nu, that is directly proportional. But if we check the wavelength, then easily we can say it is the decreasing order of wavelength. The spectroscopy, in NMR spectroscopy, we take a radio waves. In rotational spectroscopy, we take a microwaves. In vibrational or IR spectroscopy, we take the IR rays. In electronic, visible, again electronic UV for X-rays and this for gamma rays. These are the examples or application of this electromagnetic radiation. Now, when we check the spectra, so there are 4 types of energy associated with molecule. The first is electronic energy. Electronic means the transition of electron from ground state to excited state or vice versa. Vibrational energy. Vibrational energy means the center of gravity doesn't change, but it moves, it goes through to and fro motion. That is to and fro motion of the nuclei of the molecule. Third is rotational. Rotational means it rotates like this, that is center of gravity doesn't change. Translational energy, during motion if the center of gravity of the molecule it change and the molecule it goes from one position to another position. So we can say that the total amount of energy in a molecule is a sum of electronic plus vibrational plus rotational plus translational. Since the energy of translational is very less as compared to all 3, so it can be neglected. So the total amount of energy is equal to E electronic plus E vibrational plus E rotational. If we see from the Frank-Condon principle that a group of vibrational energy level associated with excited state or ground state, that is, in ground state there are vibrational energy level, let it is V0, it is V1. Same in excited state, it is V-0 and V-1. And then group of rotational energy level, these are associated with vibrational energy level. This. So it is clear that for rotation, very less amount of energy is required, that is for this higher wavelength radiation is or it may be sufficient. For vibrational, less energy is required as compared to this, so lambda it can be moved. Same from excitation from ground state to higher energy state, too much energy is required, that is for this transition radiation of short wavelength is required. And it's in this diagram it is clear that radio waves, it has a range 1 to 100 or we can say 10 meter to 1 centimeter, that is for this transition for this radiation, or microwaves are sufficient for rotational transition. Same IR for vibrational, and UV visible more energy is required, that is less lambda. So for electronic transition this is sufficient. Now Beer's-Lamberts law. This Beer's-Lamberts law, it is generally used in UV visible spectroscopy. As per this law, first Lambert law, when a monochromatic light passes through a homogeneous medium, the rate of decrease in intensity with thickness is directly proportional to intensity of the light. So what is this? Suppose there is sample and we radiate with UV radiation, UV visible radiation. Let the initial intensity of light is I naught, and after passing through medium, intensity is I. Thickness of medium is either L or X. So we can say, or path length is L or X. So initial intensity is I naught, path length is L, and this is intensity after passing through the medium. Decrease in intensity with thickness. Decrease means minus. Intensity, that is di by dl, directly proportional to intensity of the light, that is I. So if we remove this proportionality sign, so we can say that minus di by dl is equal to K. Now integrate this. Initial intensity is I naught, so thickness is 0. After passing through medium, it is I, then path length is L. When we solve this, we can say I is equal to I naught e raised to the power minus K L, where K is the proportionality constant. If we take on the basis of 10, then I, it may be I naught 10 to the power minus KL upon 2.30. So this is Lambert's law. In Beer's law, the statement is almost same, but directly proportional to intensity as well as concentration of the solution. So as per Beer's law, minus di by L is proportional to L as well as concentration. So when we solve this, it comes I is equal to I naught 10 to the power minus K dash L C 2.303. IC, sorry, this. So when we combine the both law, so it comes, you're taking the both law, I is equal to I naught 10 to the power minus epsilon C L by 2.303. So I upon I naught is equal to 10 to the power this, taking log on both sides. So we get log of I naught upon I is equal to epsilon CL, where epsilon is the extinction coefficient, C is the concentration of solution, and L is the path length or thickness of medium, and C is concentration. Log I naught upon I, it is absorbance. So A is equal to epsilon CL. This is Beer's-Lamberts law. If concentration is in mole per liter, then epsilon is known as molar absorption coefficient. And what is this A? If we check the instrumentation, then when we take a double beam spectrophotometer, at one side there is a reference solution, on other side there is a sample. Let the initial intensity is here I naught and I naught. After passing through medium, since reference solution, that is, it doesn't absorb any light, so after passing through this reference solution, intensity it remain I naught. But after passing through sample, since the few part get absorbed, it is I. So the ratio of I upon I naught, it is generally calculated, and which is called transmittance. So absorbance is log of initial upon after passing through medium, that is I naught upon I. But the basic concept which was transmittance, it is I upon I naught. So ratio of light absorbed, then after absorption divide to initial intensity. So log of I upon I naught, and A is equal to log of I naught upon I. So we can say log 1 upon T, that is minus log T. This is absorbing sample of concentration C, I naught intensity of light which is passing through this medium, path length is L, then after passing it is I. And when we draw a plot in between concentration and absorbance, it is clear that it has linear relationship. So we get a linear line passing through origin, and through this curve we can find the concentration of unknown solution, because if the solution is unknown, we can find absorbance, and through this graph, if we draw a plot against this, we can find the concentration of unknown solution. Now problem, suppose question is a compound having concentration 10 to the power minus 3 gram per liter shows absorbance 0.20, that is A is given which is 0.20, concentration is given which is 10 to the power minus 3 gram per liter, 1 centimeter cell, that is L is given which is 1 centimeter. Calculate the absorptivity. Absorptivity means extinction coefficient or epsilon. So we have to calculate epsilon, and molar absorptivity. Molar absorptivity means epsilon m. What is the basic difference? In epsilon, C should be in gram per liter, while in this C should be in mole per liter. And remember one thing, that mole is equal to weight upon molecular weight. So gram upon this. Now B.S. Lamberts law, we know that A, which is equal to log of I naught upon I, and which is equal to epsilon CL. A is given which is 0.2, epsilon calculate, we have to calculate, C 10 to the power minus 3, L 1. So from this we can find epsilon, and which is 200. Unit is A no unit, C gram per liter, L centimeter. So unit will be centimeter inverse, gram inverse, liter. Now epsilon m, the difference, she should be in mole per liter, that is 10 to the power minus 3 gram, and if we divide with molecular weight which is given 400, so it becomes mole per liter. So when we calculate epsilon m, so epsilon m is equal to A upon CL, A same, that is 0.2, but C, it will be 10 to the power minus 3 upon molecular weight which is 400, and L is 1. So if we calculate, it comes 8 into 10 to the power 4. Second, calculate absorbance if the percentage transmittance is 80. Percentage T, T means I upon I naught, which is given 80. So we can say 80 upon, if initial is 100. Since A is equal to log I naught upon I, which is equal to log 1 upon T, which is equal to log 100 by 80. So if we calculate this, it comes 0.097. Now limitation, there are two main very small limitation, that the dilute solution must be used and second, monochromatic light must be there. Now dissociation of molecule. This can be explained by the fact that dichromate ion, they shows maximum absorbance at 450 nanometer, which is orange in color, but on dilution it will be dissociate in chromate ions, but now the maximum lambda max will be 410 nanometer, which is yellow in color. This law is not valid in case of absorbing material is coagulated into small number of large units. This law shows deviation of absorbing material at the required wavelength having presence of impurities. At high concentration, it deviates due to electrostatic interaction between molecules having close proximity. And again, one more limitation, that this is not applicable in case of suspension. So here I am finishing this lecture. Thank you.